This is Lecture 17 in the FOA series on fiber optics. This lecture will be covering the basics of testing fiber optic networks with optical time domain reflectometers, OTDRs. OTDRs are an interesting piece of test equipment in that they only need access to one end of the cable to work. And what they do is they create a snapshot of the cable plant. And that snapshot can be analyzed for all sorts of useful and interesting information. OTDRs work with backscattered light. Scattering is the primary loss mechanism in fiber, and a small amount of the light, about a part per million at 1300 nanometers, is reflected back up toward the OTDR itself. So the way the OTDR works is it sends out a very high-powered light pulse down the fiber, gathers the backscattered light, averages it to reduce the signal to noise, processes it over time to display the backscatter as what we call a trace or signature of the fiber optic cable plant being tested. And this is a typical display of a fiber optic cable plant, in this case about 35 kilometers long. There's a lot of very useful information in that trace, but it's only useful if you understand the OTDR, how it works, and how to interpret traces. This is the information in the OTDR display. The vertical scale is dB, optical power. The horizontal scale is distance, calculated from time times the average speed of light in the optical fiber. The slope of the trace shows the fiber attenuation coefficient. Connectors will show reflections and loss, and splices, particularly fusion splices, will simply show loss. They're usually not reflective. The high-powered pulse of the OTDR generally overwhelms the receiver in the OTDR. So we use a launch cable with the OTDR as what some people call a pulse suppressor. It allows the OTDR time to recover from this high-powered test pulse. But the launch cable also allows us to connect to the cable under test and measure the loss of the connection to the cable under test. Standards are now also suggesting that you add a second cable at the far end, a receive cable or tail cord, and that allows you to measure the connectors on both ends of your cable plant, although it does require that you go to the far end of the cable to attach your tail cord or reference cable. Let's look at how we read an OTDR trace. Every OTDR trace has at least two markers that can be moved anywhere along the trace and are used as the measurement points for our analysis. The distance between the markers is the distance from point A to point B, where marker 1 and marker 2 are situated. The vertical scale is the loss. So if we put two markers on the simple slope of an optical fiber, it measures the loss over distance, which is the attenuation coefficient of the fiber. If we're just measuring distance, we will put the markers at the same place at two events. So in this case, we're putting them preceding the event where there's a nice sharp transition up to the reflectance peak. And so we can read the distance between the two markers as the length of that segment of the cable. In order to measure the loss between 2 points or two markers on the cable plant, we need to make sure we have a clean section of fiber in between events. As you can see, reflective events have a tendency to have a tail on the far end, and that can affect the accuracy of our measurement. So what we do is we set the two markers after the first event settles down and before the second event starts, and then we measure the attenuation coefficient between those two markers. Sometimes traces are noisy or even a little bit curvy. We can take care of that by doing what's called a least squares loss. Between the two markers, the OTDR calculates the best fit of a curve between the two and uses that to calculate the attenuation coefficient. This is the standard option on every OTDR. You'll have a 2-point loss or a least squares loss available as an option. We can measure connector or splice loss by the 2-point method too. We just put the two markers on either side of the event. In this case, it looks like a fusion splice. And we can measure the loss between the crossover points on the trace at the two markers. The problem is that there is some fiber in between the two markers caused by the resolution of the OTDR at the event. And that can have a significant loss in fiber itself and add to the measured loss. That becomes an error. So what we can do is we can do loss by least squares also. Here's how the 2-point method works on a standard event. If we put the two markers in so that the first marker is before the reflectance peak and the second marker is after the reflectance peak settles down, you can see there's a significant difference between the two markers. And the loss of the fiber in that range will be added to the loss we measure on that event, which can cause an error, making the loss appear much larger than it really is. This is especially significant on multimode fiber, where the attenuation coefficient of the fiber is much higher. To reduce this error, OTDRs can do connector or splice loss by a least squares method. What it actually does is fit a curve to the fiber before the event and after the event, and then calculate the separation of the two curves. This removes any excess loss caused by the length of fiber between the two markers and will generally give us a more accurate loss measurement. It's especially useful for very, very reflective connectors, where the tail of the reflectance peak may cause our markers to have to be set far apart. Here you can see our same event with the same two markers, but now on either side are the least squares selections that allow us to make the measurement without the contribution of the fiber in the middle. Generally speaking, this will be the most accurate way to make measurements of loss in an OTDR on either reflective events or non-reflective events like fusion splices. OTDRs are also programmed to measure the reflectance of an event. What it actually does is look at the light reflected back from the event compared to the backscatter level and calculates the actual reflectance. Like other reflectance measurements, it isn't too accurate. It's probably no better than 1 or 2 dB uncertainty. But it does give us a good indication of when an event is highly reflective, and because it's part of the overall trace of the cable plant, it shows us where the reflective events are in case we need to correct them. Here's that same highly reflective connector we were looking at earlier, set up now to make the measurement of reflectance. The left-hand marker goes before the event, and the right-hand marker goes at the peak of the event, and that's where the calculation points are for the OTDR to make the measurement. There's lots more information in an OTDR trace if we know what to look for. Here, for example, is a connection. It looks like a connection because it's a reflective event, probably in a patch panel. And you can see before the actual reflection, there's a dip in the trace. A dip in the trace indicates loss. In this case, it probably indicates the loss caused by stress to a patch cord or around the end of a cable that leads to the patch panel. We can know this by looking at the trace. We'll never know it unless we know to look at the trace very closely, spread the distance out, look very, very carefully with great detail, and know what we're looking for. And knowing what you're looking for is the secret of understanding how to use an OTDR. There are a lot more FOA lectures on YouTube that you'll find useful. Of course, there's more on testing, 2 more on OTDRs, for example, and information on insertion loss testing and long-haul testing. There's information on designing and installing fiber optic networks, and of course, a full overview of fiber optic components. Go to the FOA channel on YouTube for more information. We're the Fiber Optic Association, the Professional Society of Fiber Optics. You can find lots more technical information on our website, thefoa.org.